Right, working with scientific notation and numbers written that way. So I've got one here. I've got two scientific notated numbers multiplied together. Now, I'm allowed to move things around in a multiplication. It doesn't matter what order I do them in if they're all being multiplied. It's called the commutative law. And what I've done is that I've moved them around. So now I've got these two indices next to each other. Alright. The reason I've done that is that now I can start to use our index laws that we've learnt previously to modify this. So according to index law 1, I can take those two indexes and change them, consolidate them down to a 10 to the power of 10. Right, and that was index law 1 that says when I'm multiplying these indices, right, I can add the indexes. The reason I've done that is that now I've got one less piece. I've got this. Now, these two numbers at the front, I can do them together, just simply multiply them in a calculator or on paper, and I get 7.13. Don't forget, this bit still exists, I haven't got rid of it, so I've now got an answer of 7.13 times 10 to the 10, which is written in proper scientific notation. A space probe has been launched to travel to Neptune, alright, a distance of 4.31 times 10 to the 9 kilometres. We're given the speed of it, which is this number here, and we want to know how long it will take to get there to the nearest 1,000 hours. This time we're going to do a division because we're given the speed, we're given the distance and the speed. So if I divide the distance by the speed, I'll get how long it takes to get there. Written as a fraction, that's the same thing as a division. And I can't just jig these around and move them around like I did in the last example. So I'm going to have to do something in particular, and that thing is, first of all, I'm going to divide the numbers, or the coefficients at the front here. So the 4.31 divided by 2.5 gives me that. Now, with the indexes, the 10 to the power ofs, I can use index law 2, and I've got a 10 to the 9 divided by 10 to the 5, and index law 2 says I subtract the indexes. So I can replace all those with 10 to the 4, and now I've got that written there in scientific notation. Now I want to work out an answer in hours, so I'm going to expand this out into ordinary numbers. So that's 1.724, I'll add a few trailing zeros and move the decimal 4 places. 1, 2, 3, 4. Okay, so I'm left with 17,240, and if I round that off to the nearest 1,000 hours, it's 17,000, because that's closer to 17,000 than it is to 18,000. So 17,000 hours is our answer. Light travels at 3 times 10 to the 8 meters per second. How far will it travel in 1 minute? Well, there are 60 seconds in 1 minute, so we're going to multiply this by 60. Like I mentioned in the first example, we can change the order of the multiplication, so I can do the 3 times 60 first, and I get 180. Now, but that's not proper scientific notation, because I need to have something point something at the front. So to get this down, I'm going to turn this into scientific notation. Okay, 180 with a decimal point at the end. I'm going to move it 2 places, so that is 1.8 times 10 to the 2. So 180 in scientific notation is this. So let's just replace it and write that there. We've still got at the end of it our times 10 to the 8. Okay, and just like our previous example, now I can use index law 1 to get this down to an answer that is correct scientific notation. So it'll travel 1.8 times 10 to the 10 meters per minute.